Teresa.
Okay, thank you very much. Good afternoon to everybody. And I am very glad that we have the opportunity to host this webinar. That means I mean Warsaw University of Technology and of course NIT Warangal. We have the participant as well. And the presentation will be given, as you see here in this slide, by Dr. Nikesh Yadav from Warsaw University of Technology and by Professor Rajesh Kanaraju from Warangal. And what I should say to introducing the speakers, that maybe this is what is very important, that Dr. Nikesh was the scholar of Heritage Network, that he arrived to us from India, from Warangal, some years ago, and taking the doctorate. He successfully completed his doctorate with us, and now is employed at our university, in our institute. That in this sense, I should say, this is the confirmation of the success of the Heritage Network, and also is the confirmation that such a project now results in the continuation of the cooperation, because this seminar is the example that despite of Dr. Nikesh left Warangal, still he holds the ties and he cooperates with the staff there, and they have something together to say in the research field. And I think I shouldn't take more time, because the topic and the remaining information will be given by the speakers. Maybe just using the opportunity, I will ask only Professor Rajesh to say a few words about him. I know Dr. Nikesh quite well. However, concerning the Professor Rajesh, he will be the best person to introduce himself. Thank you.
Thank you, Teresa. So, Professor Nikesh, you can start.
Okay, first of all, thank you very much for such a nice introduction, and also thank you to Heritage. I think this is the first time I got this opportunity to thank to this Heritage Network. It was kind of very nice program. I would say that so now I joined as a faculty member in the BES Institute, Engineering Institute in Poland. And I also have a scientific grant from National Science Center. So I think my scientific career in the on the right track. So that's the thing. I think I can start with my presentation if everybody is ready.
Yeah, that's okay. Yes, please.
Can you see my screen?
Not yet.
Not yet. Okay. Participants starting here. Share screen. Yeah. Let's do. So now you can see my screen.
Yes.
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 Okay. Thank you for your confirmation. So I will be speaking about mixing problem in small scale flows. Okay. So mixing is an underlying process in chemical, pharma, and food processing industry. Efficient mixing can lower the power input and production cost of these industries. From the physical point of view, mixing enhancement means reduction of length and time scale of mixing. So in fluid, as we go towards smaller scales and smaller length, the viscous forces start to dominate over the initial forces, which results in excessive viscous dissipation, and hence mixing becomes very difficult. In such scenario, we have to rely on the molecular diffusion phenomena. And there are cases such as biofluids, plastics, long chain polymers. They have very less diffusion coefficient. So mixing is in such scenarios is very challenging. So mixing in fluid is a two-stage process. First, we do mechanical stirring, and then the intermaterial diffusion start to play the role. So we do something similar while mixing milk to our daily coffee. So what we do, we stretch the interface of milk by stirring. Okay, so what happens that when we stretch the interface of milk, so the more milk gets in contact with the more raw coffee. Okay, so that the diffusion phenomena to work faster, right? So helps somehow assist the diffusion to work faster by stirring. Stirring produces the small scales during the stretching, and that can be rapidly smoothed by diffusion. Okay, so in bottom left you can see the candy making machine. So what the candy making machine is doing is stretching and folding continuously. Something similar we do while making our pizza dough. We stretch, fold, to have a delicious candy, because the taste, we like to have homogenized things, right? So that's how the delicious candies are being made. So mixing. So the most common approach for mixing is flow turbulization. So turbulization introduce a diverse range of length and time scales in the flow, which results in rapid mixing. Turbulization is effective, but difficult to sustain, control, and predict. Hence, mixing based on turbulization is also difficult to sustain and predict. For simple flows in a control setups, we have a lot of significant advancement in their control, but a lot of ground needs to be covered to implement them. And the major problem with turbulization in the cases where we are limited by the structural strength of the device. So if our device is very sensitive to some, for example, some biofluids, we cannot use turbulization because it's going to introduce additional stress and vibration on the system. So then comes the concept of chaotic convection, which was put forward by RF in 1984. So what he proposed, like that steady flows in 3 dimensions could also result in chaotic particle trajectories. So it means that the chaos can, if we have some chaos in our advection field by introduction of baffles, obstacle, and bands, we can still have mixing. So what these baffles, obstacle, and band do, if the two particles are very close by, and then they beam through such things, they become apart in some time t. So they become spread in some time t, and we can say they are spreaded. So major disadvantage with this also is that since introduction of baffles and obstacles cause additional resistance, and when we are going to in a smaller scale, we need to reduce resistance as much as possible, because pumping become difficult in smaller scales. Because again, the surface forces or the viscous dissipation eats any inertial effect. So that's the issue with this. But still, this is widely used in microfluidic applications. This technique. So we have something novel than this. What our goal is to use hydrodynamic instability naturally occurring hydrodynamic instability to cause complex flow topology without causing much hydraulic drag. So fluid instabilities are all around us, appears in all length and time scales, and caused by magnitude of phenomena, and have a great impact on technologies and environment. So our goal is to use some surface patterns, some surface boundary modification, which can excite this hydrodynamic instability or fluid instability to create complex advection pattern that increases the mixing. This is the geometry of proposed mixing device. So what is actually is that what we take this plane channel and we replace the top and bottom wall with some corrugation, and in such a way that the corrugation doesn't change the mean opening area. So the mean opening area remains the same. The corrugations are characterized by S, which is the corrugation amplitude, L, the span-wise length of this channel, and N number of corrugation. So the first step that what we undertook is that first we find out the geometric parameter for this channel which have least hydraulic resistance. So how we proceed with that? So what we do, we take the same pressure gradient that is used in this plane channel, and we know the flow rate for this case. This is this, and we force the flow using the same pressure gradient, and then we compare the flow rates of this geometry. And if we have more flow rate, so we know that this has less hydraulic drag. So we calculate the range of geometric parameters for which we have the least resistance, or let's say more flow rate. Okay, and then on this set of geometries we perform our stability analysis to find out the critical flow conditions. So flow conditions are represented by Reynolds number, which is basically a combination of flow velocity, viscosity, and the characteristic length. So this is the summarized of all this. So what we can I can tell you about that, if we have a 9 corrugation section, 9 of this waviness or corrugation, and which has amplitude between 0.35 to 0.45, we can have more flow rate, meaning that if I use 9 of these on this, we can have more flow rate. So the hydraulic resistance decreases, right, which is quite very counterintuitive. So the hydraulic resistance decrease, flow rate increase. If we use 9 of these with the amplitude 0.35 to 45, and the most important part is the flow become unstable. So flow loses its steady laminar pattern to more complex pattern at Reynolds number 62, which is also 100 times smaller than this case. So this is quite remarkable for us towards our idea of designing such devices. So then we got interested in like whether such when this flow loses its instability due to some arbitrary disturbance and become unstable, what the real question is whether it's good for mixing or not. So to get this, we generate this Pancaro map generated by a famous French scientist. So what we do in Pancaro maps or Pancaro sections, we take a die. So we take a die of shape, let's say in a line, and we see what is the position of this die in future, right? So what we do, we are calculating, showing positions of this die in future and superimposing on a plane, and this is this kind of result of all these positions traversed by this die particle, which start from a line. So what we can see is that the die seems travel everywhere. There is no island kind of thing formed that the die cannot visit, and this is only in 74 time units. So in 74 time units, the die seems to travel everywhere. This shows the qualitative mixing. We also did quantitative and many other things, but this is the kind of more nice to show. After that, we also because since our goal is to go to microfluidics and create in a smaller scales, so there the manufacturing tolerance will start to become more important. So what happens exactly is that in a very smaller scales, it's difficult to produce perfect curves, right? Perfect sinusoidal shape. So then we tested other shapes. So we tested a range of shapes from triangular to trapezoidal to square, and what we find out that for trapezoidal of this type, the properties are almost similar to the sinusoidal groove, so they are almost close. So based on this understanding, we create this experimental setup So this is quite a big experimental setup. This is 2 meter long and around 200 centimeter wide. There are 16 of this are there, and one wall is plain, another wall has corrugation. And the question comes like, why such a big device? Because we plan to use water as a working fluid. So if because it's become cheaper with water to work on. Otherwise, we could have so it's not what we intend to do. We intend to do in a smaller scale, but this is just to first observe all this phenomena that we observe numerically. So this is setup for which our experiment is going on. And other than that, what we are interested in is that, because here in this analysis or in this study, what we took the disturbance having arbitrary disturbance size, right? So they are arbitrarily small. But then in our recent work, what we also find out the optimal disturbance shape or size. And it's more difficult to like test experimentally, but we are working on it. And thirdly, what we recently got interested into to create some external actuation mechanism which mimics this instability. So this is this thing. That's all from me. So this is all. So we do a lot of we need to do a lot of computation which are locally done on our cluster units. So they are like and this research is funded by National Science Center through a Preludium grant. Any question?
Okay, so thank you, Professor. So maybe now we can give the talk to. Thank you. We'll have the question after the two presentation.
Okay.
Okay. Yeah, maybe we can give the speech now to Professor Rajesh from NIT Warangal. Professor Rajesh, can you hear me? Maybe your micro is not open. Yes. Thank you.
Is it audible?
Yes, it's okay. And now
Professor Nikesh, maybe you can stop the screen sharing.
Yeah, okay.
And we'll give it to Professor Raju. Okay, thank you.
Is it visible?
Yes.
Yes.
Good afternoon. Thanks for the opportunity. Myself, VRK Raju, Associate Professor in Department of Mechanical Engineering at NIT Warangal. And in this particular place, we are working in these particular areas of centrifugal instability, thermal instability, combustion in IC engine, even liquid-liquid slug flow. And Dr. Nikesh used to work in this thermal instability when he was here. So in line with this particular content, today I will present something about thermal instability, one of the works carried out by some of the group members, and combustion in IC engine using your alternative fuels. This is one of the setups which we are using for our experiment. This is a 4-stroke diesel engine, computerized single cylinder 4-stroke diesel engine. This is one more engine which is multi-fuel variable compression ratio engine. So here the bulk of our work is going on because of this variable compression ratio. Then Another engine is 4-cylinder automotive CRDI, variable geometry turbocharger engine. And as of now, in this particular alternative fuels with combustion, we do have a project that is simulation and experimental evaluation of dual fuel HCCI engine by using reactivity fuels. It's a collaborative project, Indo-Thailand project, and we have 3 investigators from our place, 2 investigators from their place. And in line with this, we do have a simulation facility for this combustion modeling at our place. That is Converge software along with a post-processing software called ONSET. So these are the things which we are using as of now for our research work. Now coming to the topic concern, the first one is your thermal instability. That is onset of Rayleigh-BENARD convection with periodic boundary temperatures. Now in this particular case, when we say Rayleigh-BENARD convection, this is what we mean to say that it's a classical Rayleigh-BENARD problem where you have a horizontal plates extended up to infinity, and in between 2 horizontal plates, the fluid is confined, and the lower plate is given a heating effect. Because of that, we are getting an instability once the temperature difference goes beyond certain level, and that's where we get a convection cells which comes into picture, and that particular magnitude of difference of temperature which gives rise to a convection of cells we say as a critical Rayleigh number. But in this particular configuration, rather than giving a constant temperature at the walls, we have given a modulated temperature, that is modulation with respect to time. So the configuration whatever is given here, that is the top surface is given a temperature of C delta cos sigma t, where C is a constant which can be tuned by the user depending upon the requirement, whereas the bottom wall is given 1 plus delta cos sigma t. When I say C equal to 0, that means top plate is not at all given any temperature, 0 temperature. That is only the bottom plate is modulated. Top plate is not at all modulated with respect to temperature. When C equal to 1, we say it is in phase modulation. That means both the walls are given a modulated temperature which are in phase. When C is equal to -1, we say that is anti-phase. So these are the 3 possible ways of modulation which we can obtain. And these sort of things are in generally carried out in order to either delay the transition from laminar to turbulent, the critical point, or if you want, you can advance it. So in order to solve this, we tried 2 ways. One is linear stability analysis. Another is weakly nonlinear. Now, in both the cases, the work is carried out analytically. Now, this is a graph which shows that the results with respect to weakly nonlinear stability analysis, where it shows that when C equal to -1 and C equal to 0, that means when it is antiphase or only the lower plate is modulated, we are getting subcritical instability, in the sense the magnitude of critical Rayleigh number is less than the magnitude of critical Rayleigh number corresponding to linear stability theory. So we are getting subcritical instability for these 2 cases of C equal to -1 and C equal to 0. That means the both top and bottom plate, they are modulated antiphase, or only the bottom plate is modulated. Whereas when both the plates are in phase, that means both are modulated in place, we are getting supercritical stability. That means the flow becomes achieving a new form of laminar flow after a certain time. So these are the results with respect to your weakly nonlinear theory. But when we compare these results with respect to that of a linear theory, so these are the results with respect to linear theory for different values of Prandtl number. Whereas this is the results for the weakly nonlinear theory. So this says that the weakly nonlinear theory gives you a situation where we have a subcritical instability. And apart from that, we do have a instability which is independent of Prandtl number for a case of your weakly nonlinear theory. And in case of your weakly nonlinear theory, the critical number increases from 1684 towards your linear theory magnitude as your sigma tends to infinity. The same thing happens in case of your C equal to 0, that is only the lower plate is modulated. Here also we are getting subcritical instability, and these two natures, that is that of your antiphase and in phase, sorry, only lower plate is modulated. They are somehow similar trends. That means they start with a lower value, and as you go on increasing the value of sigma towards infinity, they will approach your linear stability critical Rayleigh number asymptotically. But the case is something different when you go for a situation where both the plates are modulated in phase. If both the plates are modulated in phase, in such cases, we will find that we are getting a supercritical stability condition. That means your critical Rayleigh number is higher than that of your linear value. That shows that your flow will eventually ends up with a new form of laminar flow after certain time beyond that critical value of 1707 in case of your linear theory. So these are some of the findings with respect to your Rayleigh-Benard convection with modulated temperature, where we have carried out both linear analysis and nonlinear analysis. And we observed that for two of the cases, the weakly nonlinear analysis confirms your subcritical instability, whereas for one case where both the plates are modulated in phase, we are getting supercritical stability condition. Coming to the other part of our research, which is in line with your alternative fuels. Now, this sort of things comes into picture because of your necessity of your fuels which can cater the needs of the society, and since the fossil fuels are depleting day by day, so all are trying for alternatives, and most of the people, they find that biofuels are, which we can say that they are the good substitutes for the fossil fuels. So in line with that, most of the people, they tried to characterize the fuels, and they found out that the maybe calorific values on the lower side as compared to that of your fossil fuels, but still this can be utilized in the existing engines and without sacrificing that much of performance. So that's where this sort of things came into picture. And when we say that the biofuels, most of the time the biofuels are pure vegetable oils, or it can be from your animal fats. So depending upon that, it may be edible or it may be non-edible. And since in our place, our consumption is there on a higher side with respect to edible, so there is some restriction. So most of the people, they are trying here with respect to non-edible oils such as jatropha, neem oil, castor oil, and they are trying to have a good alternative for the existing fossil fuels. So in order to carry out the research in this particular line using alternative fuels, in generally we do this with the existing engine, and we will try to see that how the performance is varying compared to the traditional diesel fuel. Then we carry out most of the performance analysis using a simulation, and then once we try to come up with a better solution, that is what we say optimized solution with respect to performance as well as stringent emission norms. And depending upon that, we can suggest that if we will use a particular fuel, then what will be the operating parameters so that we can get a better performance as well as emission norms satisfied as per the government of that particular place where you are using this. So this is a particular set of which is a variable compression engine. And in this particular case, we can run this engine either in diesel as the working fuel or the petrol. Both the options are available with a single engine. We have to change only the cylinder head, and as well as we can control the compression ratio. We can control the start of injection. So these are some of the facilities which are available with the existing engine, where we can carry out our operation, and the output will be given in terms of P theta, that is pressure versus crank angle, temperature versus crank angle, through a particular software connected to a system. And once we get the data from the engine, we compare the data with that numerical simulation for the same engine. And once we validate our numerical model, then we carry out for the other parameters for which we want to optimize. So this shows the variation of your pressure with respect to crank angle, and the yellow line shows the variation of the pressure with respect to crank angle for a baseline engine. That means the engine which is predefined at a particular setup. Against that, this is the curve. But once we go for an optimized value, because the objective is to run the same engine, but now with a biodiesel. Now this biodiesel, what we are using in this case is PB20. That means 20% by volume biodiesel. Here in this case, we have used the Pongamia oil, and 80% by volume as the diesel as such. So with respect to that, the baseline data shows a curve of this nature, that is the orange color curve for the P theta diagram. But when we went with the optimized value in the sense which gives you the optimum performance with respect to output as well as your emission norms, then we found that the peak pressure is increased, and quite obviously it moves towards the left side. That means the peak pressure is obtained around or before just top dead center, and the temperature in case of your optimized case is on a lower side compared to the baseline. That's where we are getting the advantage with respect to the emissions, because the in-cylinder temperature is on a lower side, ensures less amount of NOx emission, and which is our objective, because to satisfy the stringent emission norms. Then compare with respect to your performance analysis, that is the emission norms. Like we can see that with respect to your baseline data, the optimized value gives you an emission in the order of 10 to 2 into 10 to the power 7 compared to the baseline data of your 1 into 10 to the power -6. That means 80% reduction in NOx. Similarly, soot also, there is a decrease in soot at the emission, which is also in the order of 2 into 10 to the power -6 compared to your baseline data of your around 5 into 10 to the power -6. So around 60% reduction compared to the baseline. And compared to hydrocarbons, that is unburned hydrocarbons, there also we are finding that in case of your optimized VCR engine, that is variable compression engine with Pongamia as the biodiesel, almost all the hydrocarbons are utilized. That means the complete combustion is ensured. So that's why the particulate matter which comes out of this emission will be on a lower side. And the same trend we are getting for your CO also, carbon monoxide, that also on a lower side compared to the baseline. So what we tried is we want to get a optimized value. So for that, we carried out our optimized calculation using the software which is available with us, combustion software. Now this gives a comparison with your baseline configuration to that of your optimized configuration. Now this shows your variation of your fuel distribution within a cylinder at different crank angles. Now the blue color shows the lower value of equivalence ratio. Red color shows the higher value of equivalence ratio. And our target is to have equivalence ratio in the range of 0.7. That is what somehow midway, which is having green color. So if you have equivalence ratio is uniform throughout the domain, that means you can ensure that there is no zone of low fuel region or there is no zone of rich fuel region. So we want a uniform fuel distribution. So once we go for the optimized condition compared to the baseline configuration, you will find that for all the cases, that is whatever is the crank angle position, for all the cases, you will find that target fuel distribution index is higher compared to that of your baseline in all the cases, which ensures that the fuel distribution is quite uniform throughout the domain. That means you don't have any pockets where you have a rich fuel or there is no pockets where you have a lean fuel. If you have a rich fuel, then you will get some particulate matters. If you have a lean fuel, the temperature increases, you have a NOx condition. So the target is to minimize the variation as such. That means uniform variation has to be obtained throughout the domain. So that way, our optimized value, whatever we have obtained for our operating parameters using our optimized solver, ensures that the target fuel distribution is around 90%. That means 90% of the area is filled with required equivalence ratio compared to the baseline data of 64%. So that also confirms that using a existing engine for diesel can be utilized for a biodiesel, but we have to suitably modify some of the parameters so that you can use the same for the biodiesel blends, and in turn you can get the same performance as well as emissions, or better emission norms can be satisfied with this particular engine with biodiesel as a substitute. So this is with Pongamia as the biodiesel fuel. So same way, this is the comparison of your temperature distribution, because if your temperature is on a higher side, that shows that the NOx emission will be on a higher side. So all the time the target is that the temperature should be on a lower side as minimum as possible. So that also confirms from this figure, that is for the optimized case, the temperature is in the order of 1675, whereas for this particular case, the pockets where you have a red color zones having a temperature in the order of 1800 Kelvin. So that shows that the NOx emissions are also on a lower side with this particular engine. In line with that, we also work with some alcohol-based fuel blends. Now, in case of your alcohol-based fuel blends, the advantage is the alcohols are having a higher value of latent heat. So most of the time, we are getting advantage of low cylinder temperature. Here, these alcohols can also be derived from the sugarcane bagasse or corn stalks or rice straw. So that is one of the advantages which we can achieve those alcohols. But again, in alcohols, we have a varieties of chains. If you have a lower chain, which are mostly used as a substitute for the traditional fuel, that is methanol or ethanol, they are widely used for the substitute for the IC engine fuels, but they are having some demerits with that. That is, they are having lower chain alcohols, are having lower energy density and inferior cetane number compared to that of your diesel. So that is one disadvantage with your lower chain alcohol. So we tried for the higher chain alcohol like butanol. So this particular results whatever presented here is in line with your butanol as our substitute for the engine with diesel as the primary fuel. So in this particular problem, we tried for different combination of butanol percentage in the blend. Now the figure whatever we are showing it here is with butanol 00 means it is pure diesel. Butanol 20 means 20% butanol, 80% diesel. Like that, if butanol 40 means 40% butanol, 60% diesel. So the first graph which can be seen from here, which shows that with the help of your butanol, the in-cylinder pressure P theta variation is almost similar, but the peak occurs little bit after TDC compared to the other or only diesel blend or only diesel fuel. This is quite obvious because once you add butanol alcohol-based fuels, then since the latent heat of vaporization on a higher side, so it absorbs more amount of heat to vaporize. So in cylinder temperature decreases. So combustion gets little delayed, because of which you are getting the peak little bit after the top dead center. And if you compare with your other parameters, like here we have used EGR, that is exhaust gas recirculation. With increasing the value of your EGR, your in-cylinder pressure decreases, and that is quite obvious because the portion of your cylinder is occupied by the exhaust gas itself rather than the fresh charge. So that's why the in-cylinder temperature pressure cannot increase beyond certain level. And if you go on increasing the compression ratio, that is also one of the parameter which usually we tune. And we says that with increasing the in-cylinder pressure, compression ratio, the in-cylinder pressure increases. Quite obvious, that depends upon our PB diagram and the pressure volume relation. And these are the some of the graphs which we are using in this particular experiment in line with those shown above, like in pressure cylinder for different value, different compositions of butanol and different compositions of EGR, which shows that with the addition of your EGR, the in-cylinder pressure decreases, and at the same time, when you increase the blend butanol percentage, there also here it shows that the in-cylinder pressure is almost similar, but there will be little bit of variation. But the benefit what we are getting is with respect to your compression ratio. Here we can see that when you are increasing the compression ratio, the butanol 40 gives you a higher in-cylinder pressure compared to your pure diesel. And this shows your effect of operating condition on NOx and soot emission. That is what the main objective most of our research outcomes, because NOx has to be on a lower side. So you can see that when you are using the butanol for all the loads, you will find that the BU40 gives you the lower value of NOx at the exit compared to the diesel. So that itself shows that using butanol as a alternative fuels will ensure that NOx will reduce. But if you want to reduce it further, you can go for a EGR. EGR can be used for pure diesel also, and that we are doing that with pure diesel. But with your alcohol as one of the additives, means the biofuels, if you are using your EGR, that further decreases your NOx emission, which is necessary for us, because when you go for a higher compression ratio, in generally NOx increases compared to lower compression ratio. If you go for higher compression ratio, if NOx increases beyond the limit of what you require, in such cases, it's better to go for a EGR along with your alcohol-based additives. So this is unburnt hydrocarbon. That also shows a similar trend compared to that of your pure diesel. So we can say that ISFC, that is indicated specific fuel consumption, and soot was most influenced by the compression ratio. That is, compression ratio plays a vital role with respect to these two operating parameter outputs, ISFC and soot. EGR and SOI, that is start of ignition, has most influence factor on NOx emission. That has to be controlled, tuned properly. The optimized butanol 20 case reduces the soot, NOx as well as ISFC. That is what the objective is, to reduce all these three things. This is with respect to emission, this is with respect to performance. So if you can reduce all the three, then that will be good for us. So we tried for that. So this TFDI increase for optimized BU20 case compared with the baseline configuration, whatever I have shown there, further confirms that we are trying to achieve some sort of a HCCI. I won't say that we are getting HCCI combustion, but we are trying to get towards HCCI combustion using this sort of a optimized technique. So in near future, that can say that with these existing engines, with alternative fuels, with some modification with respect to operating parameter, we can achieve the required emission norms as well as performance. So that is something about my research at this particular place. Thanks for your time. If anything.
Okay, thank you, Professor Rajesh. And now we have some minutes for a question. Maybe it can be also discussion between yourself, the two professors, to explain what kind of cooperation it is possible to do with the two institutions. Anything like this, okay? Yeah, maybe Nikesh, you are more specialized than us.
We start to collaborate because Professor Raju has a lot of experience in thermal instability, and in our department at Poland in Warsaw University is basically fluids. So we do a lot of fluids simulation and experiment. So we have wind tunnel, which NIT Warangal don't have. So we have massive wind tunnel, dates back to before World War II. It's recently refurbished, and so we have few wind tunnels. We have transonic wind tunnels. In that area, and it's difficult to construct, or very expensive also, need millions of. In this aspect, we have scope that we can share with NIT Warangal. This type of thing. We have supercomputer in our department, a small, not a big one, but a small one, and that's also that was also an asset to share. We start to collaborate. We have we are start to work because. Professor Raju can help us to, with this thermal aspect, and also because combustion is also mixing. In that aspect, we can collaborate on that, and to solve some multi-physics problem. We soon will have some publications together. And we plan to write this. There is a scope of under NAWA. It's a Polish institution to have India-Poland grant, which was it was come 2 years before in 2020. We also write this grant, but so we plan to write this grant again. So this will allow us to have a mobility between two institutions. So that's what I see.
Thank you for the answer. Maybe we have Nivita who show his hand to have a question. Nivita, if you hear us, your micro is not open. No, maybe he forgets question. No. Yeah, Teresa, please. We can wait for Nivita.
Thank you. That I should say that I like both presentations, and especially the biofuel. This is something which we really need in our days, because there is a lot of talk about the pollution, about the damage of the natural environment. But I have the question to Dr. Nikesh, that you presented the analyzing the instabilities. And my question that I got the impression, maybe wrong, that all what you had done, it was using the simulation. That my question is related to this impression, that if you confirmed your result by some experiments, or this is only the simulation. Could you please respond this question?
Yes, thank you for the question. It's a very good question. So yeah, so this is all basically numerical simulation. The experiment setup is already built. It's built already 6 months. So I will tell you that this getting this instability, if we get once we experimentally validated it, for sure will come in the many newspaper. So it will be in Fluid Mechanics Society. It will be I think something big happen in this decade. So because so this instability, we're trying to achieve this instability at a very lower threshold of energy. So the instability is what we know. They are sensitive to disturbances. The famous experiment of Reynolds, which shows us that there are differences, laminar, turbulence, and transition. So in his experiment, what he did, he built a very big experiment setup, and he calculated parameters in day, and he found, let's say, 10,000. And then he checked this experiment in night when there was no noise, and the results were different. And it's make him puzzled for a few days that why is so. And then he get to realize that even acoustics that's going around influence this instability, because in this world is the reality. And when we think, then he take account of this. So again, coming back to our instance, so our experiment setup is our instability is very sensitive to very smallness of disturbance. So there was a very small experiment done at PAN from Boensky and at Kowalski. So they get something, some nuisance of this instability. It's not a so we trying to achieve something similar. I just wanted to again state, like, to emphasize that this is the difficult. So we already have experiment, and we will get it. We'll plan to, and after that, I perform further more numerical studies. So we have with this experiment, if we don't exceed, we also start to have a plan B. So we have other we plan to have because the issue with the instability grows very slowly. So we might need in this our setup not able to observe it, because we need to have a very big setup. And which is maybe this will become small enough. So I start to work on. So I have another solution for it, and so definitely we will get it, and it will be a very big kind of moment or achievement for our institution and our Poland. Thank you.
Okay, thank you. Perfect. Thank you. Very nice perspective. And may I ask now the question to Professor Raju? Yes?
Yeah,
okay.
Please go ahead.
Yes. You presented a very nice testing results of the efficiency of the engine. Depends on the fixing of the arrangement. But I was also not sure if those results which was showing to us using the drawings and the color with the colors distribution, that was by simulation. And my question is, if you all justified, somehow similar question as to Nikesh, if you had justified those results using your experimental stage or not?
Yeah. We do have an experimental setup, and we used to validate all our numerical code prior. That is what we say validation of our numerical code as the first step for any particular work what we undertake. But the problem with the experimental is having limited operating variables. We cannot tune the existing engine to varieties of variables. So that's where we come into simulation for study the effect of the variable on the performance. Once we confirm that which is the optimized, again we will try to verify the same with the experiment. There will be some errors, differences, but we do so.
Yes, thank you. Thank you, because I understand that some parameters or some features you are not able to measure on the engine.
No.
Like
Yeah, I accept.
yes, that is impossible. That only you can observe the output. Yes, thank you very much.
Welcome, ma'am.
Okay. So maybe Nivita, you have still the question? No. Okay. We have someone who. Okay. Thank you very much.
Thank you.
And now we can close the webinar, and we hope that we will see you, and I wish you a long cooperation in this topic and in other topic. Thank you very much.
Thank you.
Thank you. Thank
Bye.
you for the opportunity.
Thank
Bye.
you to the presenters.
Thank you very much.